Hello, everyone. So in today's talk here, we're going to talk about some of the challenges of operationalizing machine learning, putting machine learning into production and keeping it in production. We're going to talk about it specifically in an edge context with Spark. So we're going to talk about the combined challenges therein. Because it's the last talk of the day, we're going to try to keep the slides relatively short, and about half of our time we'll just do a demo, so that might be more fun. So just the first thing is, this is a study that was done by the McKinsey Global Institute, and what it talks about is what's going on with AI investments. And the basic idea here is, lots and lots of people are trying out AI, and they're making all sorts of investments in trying out machine learning and deep learning and different flavors therein. But what this study showed is that, at least as of today, a good chunk of this stuff is not moving beyond the experimental stage. So people are seeing success in doing experiments, but they're having real difficulty putting those experiments into production and getting them kind of over the hurdle into a real operational environment. But it also shows that people who did that actually saw benefits. So they're seeing notable profit margins for those companies that were able to bring AI into an operational reality, but many people are challenged with doing that. So then, there are many reasons why this is the case. So one of them is just the sheer difficulties of, deploying and managing machine learning and all variants in production. There are many reasons. Some of it is the fact that, at the very least, two very different types of skill sets need to collaborate. This has been experienced in other complex apps like databases in the past, but there are unique challenges with machine learning because, on one hand, you have data scientists who are have strong algorithmic expertise, but putting something into production also requires ops capabilities and the collaboration between these teams. Machine learning, as you guys very well know, is very specific classes of algorithms, many of which are, while technically reproducible, have so many interdependencies upon data and so forth that their behavior is, analyzing and diagnosing their behavior is a unique difficulty that has to be addressed. And even though there are many DevOps solutions right now for very quick turn updates to applications, as well as tools to manage and monitor complex apps, many of those tools don't really address the uniqueness that's brought on by machine learning types of algorithms. So to bring this in combination with what are the additional kind of challenges brought on by edge types of topologies, the first thing to recognize is that the word edge doesn't mean the same thing to everybody. It means lots of different things to lots of people, but in many cases it means some kind of a distributed topology with various degrees of resources that are connected in all sorts of ways, and they range everywhere from things, sensors, little devices, to computers in the middle, to collections of computers closer to the center. The resources are varied, the scales vary, and there's a lot of heterogeneity, a lot of disconnected operation, a lot of complex communications, and things of that ilk. So starting with machine learning and its challenges, whether you have an edge or not, what you really need is really a life cycle for operational machine learning, and that life cycle kind of spans between data science, which is where algorithms get developed and new algorithms get tested, to what happens in production, whether that is purely scoring and model serving or inference, or whether it means retraining. There's collaboration that's required between data scientists, operations teams, and data engineers, as well as the need to really close the loop and bring new algorithms into production and continuously improve the ones that are already in production. So really, in order to do an operational ML, you need to have sort of a tool chain that can facilitate some of these things, allow complex configurations to be diagnosed jointly by both operations people as well as data scientists, how to monitor and diagnose machine learning pipelines, look for situations like model and data drift, monitor their behavior from the point of view of specific metrics, as well as the more nuts and bolts aspects of orchestrating pipelines, figuring out what's up, what's down, what's resource consuming, and so forth. So now when you couple this with some of the edge scenarios, and recognizing that in many edge use cases, data originates at a sensor level device, and then subfractions of it migrate over time into cloud, and you can have a number of different things. So in edge use cases like industrial IoT, For example, you might have the need to process data very close to the physical device. You may have the need, for example, to detect anomalies very close to the physical device if you're doing things like smart building security and so forth. At the same time, you have collections of data that flow close into the cloud where model training can occur, larger aggregates of data sets are available to develop better models that then have to be pushed back to the edge devices and so forth. And you basically have a fairly distributed environment with multiple layers of topology in it where you want to really run a single machine learning application, but different pipelines could be running in different places. So what we are talking about in this talk today is how to handle that production life cycle for the topologies that span from cloud to edge. And by the complete production life cycle, we mean things like the continuous integration and deployment in combination with DevOps tools and software repositories like Git, for example, as well as the orchestration of machine learning pipelines, pushing out of models from training to inference, monitoring and diagnostics, and the ability to govern and, where appropriate, understand the versions of models that may have been developed. So the approach that we have taken to this is a software runtime that basically kind of works in a sort of a distributed environment. So we attach to various types of analytic engines. Today we're going to be speaking obviously heavily about Spark. And so you can run these, in this case specifically Spark, in various locations, and they can be geographically distributed. And we attach agents to those. Those agents are bidirectional and perform everything from launching of pipelines to monitoring of pipelines, and you'll see both of those in the demo. The agents connect to a server, which can be somewhere within network connectivity. So in a distributed topology, for example, you can have different instances of Spark running in different places, each with their own agent, and then everything communicating with a scale-out, highly available server. And then this architecture handles things like bandwidth mismatches, disconnection, and things of that nature while your pipelines are running. So you can have a variety of pipelines running in different places. And then to enable different folks like data scientists and ops to collaborate, people can access the behavior and monitor the behavior of these pipelines through UIs and REST interfaces and things of that ilk. So in order to facilitate how to describe such a thing, we've introduced a sort of an operational abstraction that we call an overlay network for pipelines. And the basic idea here is that if you have different pipelines that are running in different places that are related to each other, maybe some edge pipelines are running and they are receiving models from a cloud training pipeline, then you can express your topology as a graph. And this graph is a graph of pipelines. And then you can show through the graph how different pipelines are related and what the purpose of each one of them is. And then when this graph gets deployed, it actually gets deployed across a physical topology that can span a heterogeneous array of devices. So as an example, a graph can be deployed where some of it is running say in a data center, others are running on, say, branch office, computers. Because we're talking about Spark, we are talking really about, at least in our environment, we have talked about running things that are at the very least a single core machine for the edge. So we are personally not going into very extreme edge kind of scenarios, but it is certainly possible. So what we're basically talking about is that you define this overlay network, like a graph topology, where you say, what are my pipelines, and what do they do, and how do they relate to each other? And then at runtime, when they get launched or executed, they get mapped onto a physical distributed topology of resources. Examples of pipelines these are two simple examples that are Spark ML pipelines. One of them is a training pipeline. It does some data transformations, starts with a CSV, goes through, and runs, for example, some simple feature engineering and then some logistic regression training. The output of that training is a PMML model, which can be fed into a matching inference pipeline, which will perform the same kinds of transformations. It will run on data that may be occurring live in the field and will perform predictions based upon the model, and we'll send those predictions into a file. So that's an example of the kind of pipelines that you could have in this graph. So in order to bring these pipelines into our environment, you create a JSON file that describes how those pipelines are related. So specifically, the overlay network is described as a JSON file. You bring in the actual code from these individual pipelines, and the template tells us how it's related. You can instrument this code as you like to report whatever kind of statistics you would like to report. And then these statistics are gathered while the pipelines are running and are stored in a database that we then later use for visualization and such. So specifically, how we integrate with Spark is through Spark native interfaces. So the key thing here is that we don't modify Spark. So you can basically bring in any program that will run on Spark for any, from any of the publicly available programs to anything that you wrote. Our statistics monitoring also works within the Spark infrastructure. So essentially, you can run the program without us as well if you wanted to debug. But when it's running with our runtime in place, then it will essentially send the statistics to places where we can then do post-processing on it. And our agent basically communicates with the Spark instances as they're running in these various scenarios. So I'm going to hand it over to Vinay, who's going to show you the demo that we're about to run, and then he will run the demo.
Hey, everyone. So Nisha just described this whole concept of an ML application and how we've developed this concept of a graph that maps itself to this ML application. So if you look at this specifically in the context of a center and edge, so imagine that you have the training of your model that happens in the cloud. So let's say you have a big data set. So you need the resources of the cloud to train the model. So, so we define so this is sort of like it's not exactly a DAG, it's cyclic in nature. So the source of the model here is the one node on the left, which is the cloud, represents the cloud. And imagine every other hexagon that you see in this graph, each represents an edge node. And what we've done in this demo is sort of mimic a real-world edge kind of clustering scenario where edges are usually grouped. So for example, let's say you have zones in North America, and then you combine certain edge devices into zones across your continent. So in this case, if you have 4 zones and you have edge devices that are sort of clustered across these zones, each of them independently want to probably feed data from their local data sources and infer on the models generated in the cloud. So this graph that we've built ensures that this periodic retraining and re-inference of data and models occur, and models are deployed as the arrows of this graph indicate. So this demo will walk you through a simple classification model training and inferring of this classification model on a set of edge devices. Okay, so let's skip past the login and all of that. Okay, so let me pause here. So as we described earlier, we have the concept of an agent. So an agent is basically a platform agnostic entity that can understand and interpret any machine learning engine that we interact with. So in the case that I'm going to demonstrate here, each of these agents speak to one Spark environment. So in the case of Edge, imagine a single x86, single node x86 server that is capable of running Spark. So our agent is sort of a one-to-one mapping with each of these edge devices that can deploy Spark, can monitor the Spark, can control the Spark jobs and analyze and extract the statistics and data out of that, and present this to the user in for monitoring ML and monitoring their progress. So each of these agents, you sort of set it up in our system, as in we have a register agent mechanism to do that. And as we progress through this, we'll talk about how we next. I showed you earlier this concept of zones. So effectively, the agents that we've registered are now going to be clustered into zones. So the next step of the building process will be, now that you registered your agents, you create the groups or the zones that they belong to. So that is mostly a virtual concept that we've defined. So in this case, and sort of what the slide itself showed, you have one zone A that has 4 agents, zone B and C of 2 agents each, and you have a training cluster which represents its own group. So this is the second sort of step that you do before you construct your entire graph. So I'd also like to point out now that there is the infrastructure side of this, and then there is the actual compute side of this. So we've got this components that you can upload to our system, and Nisha showed that in the slide. So you can create your own Spark Python jobs or Spark Scala programs and upload it to our system, and that sort of becomes an entity in our ML pipeline that you can now deploy on each edge device. So in this case, I just picked an example of a few PySpark programs. So you can, so we'll probably be using the logistic regression, which I don't know, hasn't shown up here for some reason. Okay, so this is the pipeline I was talking about. So the components that you've now uploaded to the program are now connected together to form an inference or a training pipeline. So if I show you, okay, so let's pick the training program. So the training pipeline is similar to what we showed in the slide. So it ingests data from a CSV, which could be on a HDFS or any other clustered data file system, which is then fed to a Spark pipeline. So all of these are Spark components built in MLlib and SparkML, sorry. So this is a standard training pipeline, which will then become what the cloud's training agent handles. So you have an option of choosing all your parameters, all the variables and mechanisms that your training program exposes. And let me just forward through this. So similarly, for the inference pipeline, you have an option of reading from a CSV, processing it through an inference pipeline, and writing its results to an RDD file. Okay, so let me skip through all this. Okay. So now, Okay, so now we come to the point where we construct the graph that I started with, right? So we've registered agents, we've clustered the edge devices into zones, we've defined pipelines that should run on each of them, and now we bring everything together and create the ion or the graph that we're talking about. So give it a name. Okay. So now I pick a node. This you select the group that you want to run it on. So this is a training node. You select the pipeline, which is going to be our training pipeline. And you can set the schedule at which you want to run this at. So for the purpose of this demo, I'm just going to do a couple of minutes. So which means it's periodically running every 2 minutes and retraining itself. And now you connect the training to, so the model is now propagating to the edge devices, which is now, in this case, zone A. So a set of agents that span one of the zones in the North America cluster that we talked about. And of course, the same thing, you select the inference pipeline, you select the schedule, and I'm just going to skip because it's going to be repetitive. So we just do this for all the 4 zones we spoke about. Okay, so this is the graph that effectively represents the cloud or center to edge mechanisms and entities. So, okay, so fine. So now that we've set up this graph, there are some certain policies you can apply to them. So whenever models flow, you have an option of selecting the policy that you want that the model gets deployed with. So if it's a manual policy, you always expect an operator to approve the model before it gets deployed to all these edge devices. And this is standard practice because people want to evaluate a model, maybe want to look at its statistics or measure its, if its accuracy is improved, or run some evaluation offline before you decide to actually deploy them in the edge scenarios where they actually infer on real data. Okay, so now that this is set up, we launch it, and the launch basically, effectively now what it does is has now triggered all these Spark jobs on the training across every agent on all the edge devices, and all of them are buzzing and running right now. And our graph entity and the agents at every location is sort of doing its work of pinging them and making sure they're up and grabbing stats and grabbing status and so on. And what I'd also want to, so I'm going to skip through a lot of details of what happens. Let's just quickly look at some other interesting things here. So this says the model is ready, which means training is completed. So another a facet that we've, so this is the approval process where because we selected a manual policy, you have to have an operator. Okay, so now let's stop here. So given that we've said we wanted to examine the model before it gets deployed to the edge devices, we have an option of looking at statistics that the model has been trained with. So this lets you go and look at its, so in this case, we're looking at the confusion matrix, and then maybe all this, the numbers look good. This model is exactly what we wanted it to do. And at this point, the model looks good, so we can actually approve it, right? Okay, so once it's approved, I'm just going to skip through a lot of this. Okay, once it's approved and it's been deployed, this is when our monitoring kicks in, and you can examine. So the cluster that we've shown is actually scaled out.
Yeah, the visual is not
oh, it's not coming through well. Oh, yikes. UI is probably a lot better than that. All right, so as I said, so the scale of this center to edge network requires constant monitoring from the agents. And using this dashboard, you have a single point where you can examine the entire cluster and the entire network. And so we have sort of this health view and a data science view, and health view is probably a broad, so it gives you high-level numbers and KPIs and heat map of what's happening on every device. So in this case, we're going to look at, so if you look at I hope my mouse is pointing there, right? So here you have every edge device that as a drop-down menu, so you can choose which of the edge devices you want to monitor. So for each of them, we've captured the flow of data coming in, so it gives you a heat map of what's going on. We compare it with the histograms generated from the training device, so that gives you an idea of how well your model is inferring. And you can do this for every single inference device that you've connected in your edge network. Let me skip through all of this. So we also have this thing called a logical event capture, so it captures all your events across time. So not necessarily chronologically, but then we've sort of built, because it's a graph and it's a cyclic graph, we have a nature of logical event ordering in our graph. So for example, a model is generated somewhere, it's inferred on somewhere, you have a prediction generated somewhere. Before that, you have an approval. So there is a sequence of logical events that has led to a point, and we've captured these as an event sequence for somebody to view. Okay. So, and the other aspect of this is what we're calling the data science view, which is a deep down into this network. So in this case, if you look at the graph here, this is your entire ion structure, or the graph structure, and it represents all the edge and center devices. So using this interactive sort of graphic, you can choose every one of your edge devices that you want to monitor for deep ML statistics. So this is stuff that your training or inference program has emitted as part of its statistics and monitoring. So we have an API that lets you expose any stat that you want during the duration of your inference or training pipeline, and these are all displayed as a graphic for you to visualize here. So, right, and all of this is, again, given that we've integrated well with Spark, this is all via Spark's accumulators. So we sort of tap into Spark's accumulator interface to constantly stream the values coming out of there, map them into a graphic format, and show them here. So essentially, any Spark program that can write its statistics to an accumulator is probably going to read from here. Okay, so and we also, for example, we also capture logs coming out of Spark. So let's say one of the edge devices is sort of, you see a failure. You can also go and examine the Spark logs coming out of each of these edge devices. So that's what you see here, and maybe if I just fast forward a bit, right. So for any of these agents you want to examine the logs, you can go and search through them, scan through them, download the logs, look at it in detail, and so on. Okay, so I know I'm keeping you all from going home. Let me fast forward a little more. Okay, so this is a feature that we'd like to we've called timeline capture. It's basically a snapshot. I mean, for want of a better word, it's only a snapshot, but a sequence or a continuous snapshot over a period of time. So for example, here you're training and you're inferring. So for the entire duration of the training going on and inference going on, we've sort of kept a timeline of events that happened across that time. So you can always, once you've captured the timeline, you can go back at a point in time and examine statistics. For example, a specific model that you deployed and you find out later on that it's that is performed poorly, you can go back in time and examine its statistics at the point. So in this case, I've just taken an example of a timeline for about 10 minutes. Okay. I go and view the timeline. Yep, it's created. Yes, I know that. And I'm going to browse it. Yep, okay. So when you go to browse a timeline, this is effectively like a recording of everything that has happened in your ML application. So as you can see, there is a time bar there, so you can adjust the time, look at look at the pattern of data that happened at some point in time, look at the sequence of events that happened during a duration in time that you've captured. And effectively, it's as good as viewing the entire thing live, except that now you've gone back in time, so which is probably why we called it timeline capture. Cool. So and also, just like we showed you a data science view where you have a detailed, in-depth view of all statistics in your ML application, the timeline capture also gives you access to all of that. So for example, this confusion matrix was something that you generated at some 6 a.m. yesterday, and the timeline capture lets you go back in time and examine the values as they were then. Cool, and same thing applies to logs. So effectively, it's as good as you were at the point when it happened. So all your logs and Spark, statistics, and so on are all captured. Okay, so let me pause here. Let me stop here. And
yeah, so I think the basic. So the basic. Thanks, Vinay. So the basic idea is that so if you look at kind of the sort of the kind of topology, and these kinds of topologies can occur at scale when you have an edge device, but they actually also present in a smaller scale inside a data center where you may have multiple machines. What we've shown here is essentially a way to kind of look at the life cycle of a series of pipelines, understand how they're related to each other, and be able to see in the same place a continuous or organized timeline of what happens in these pipelines. This can be particularly useful if you're trying to diagnose stuff and you're trying to see what happened, and you want to see everything from the behavior of the machine learning algorithm to what happened in the engine underneath with the logs and so forth. It becomes doubly useful when these things are geographically distributed and you really want to see a collective view of everything that happened, and you want to be able to share those views between data scientists and and operations people and the like. So we wanted to just kind of show you a quick demo of how that plays out. So I think that's all that we had, and we'd be happy to take any questions.
Hi, thank you for your talk. I was curious on how do we deploy these Spark models to the edge? Like what is the representation serialization of these models? Is it something custom, or is it something that you leverage from Spark? Because I know there are difficulties trying to deploy these out of the box. Spark was really defined for transformations in data frames, not really a kind of isolated predictions.
Right. So it's a very fair question. So what we've done is sort of a combination of we work with both standard format models. So PMML is a common format for Spark. We also allow people to have custom models. So when you create a model in our system or you upload a model, you can identify it as a binary model, which is basically a clue that we don't know what it is. And so for binary models, we do the mechanisms of pushing it and giving it to those running pipelines, but we don't try to interpret it. So particularly in edge devices, for example, particularly those that are doing various kinds of fault anomaly detection, sometimes they combine rules engines with classic machine learning inference, so the model formats can be custom.